gravitational waves. So if you've already heard about it, you may not, there's no great data to present, unfortunately. But so if you already know the field, you won't necessarily learn a whole lot. But if you don't know much about the field, it's sort of at the introductory level. So I'll talk about what gravitational waves are, where they come from, a survey of the kind of astrophysical sources that might produce gravitational waves, and concentrate a little bit on my favorite one, which is compact binary coalescence, and what we'll learn about the physics and astrophysics, the physics of gravitational waves and the astrophysics of their sources. And what I'd like to do, but can't, well, Einstein predicted the existence of gravitational waves in 1916, and here, 98 years later, we still haven't even detected gravitational waves in any convincing way at all. What I'd really like to be able to do is, in this talk, announce the discovery of gravitational waves. But I can't do it. I'm sorry to say that I will have no discovery to report today. On the other hand, well, the centennial of that prediction is coming up in a couple of years, and there's a fair chance that by 2016, gravitational waves will be discovered by LIGO or maybe by other kinds of detectors.
For all practical purposes, binary pulsar is a detection of gravitational waves. It's not fair to say that we have not seen them.
Directly.
You guys want to come up here? So I'm going to talk a little bit about the indirect detection of gravitational waves as well. But it would be nice to actually directly detect gravitational waves now, or I hope it will be possible in about 2 years, but it might take a little bit longer than that. I'll give you a time scale. But I'm pretty confident that we will start detecting gravitational waves directly and start studying their properties and their sources sometime in the next few years. So I hope to convince you that that's a realistic possibility. Okay, so first my one-slide introduction to what gravitational waves are. Probably most of you have seen like an embedding diagram like this one over here. Here's space or space-time, but let's just say space and spatial distribution around a massive object like the sun. And in Einstein's theory, a massive object distorts the space around it, like a little dimple like this, and then a test mass, like the Earth over here, will move in a straight line in this curved space-time, and it'll form an almost perfect Keplerian ellipse. And so all of Newtonian physics can be nicely explained, and even some deviations from Newtonian Keplerian type motion, which have been already observed, which can be explained using Einstein's theory. And it's a beautiful theory. It says that the curvature of space and time responds to the presence of matter and energy. And then the motion of matter and energy responds to the curvature of space and time. And so that beautiful symmetry is what gives our modern description of gravity as being the curvature of space-time. And what it essentially means is that an object like a test mass will move in a straight line in that curved space, just as has been observed in our solar system very precisely. But that's just a static picture, and that's just one star. And if you imagine changing gravitational field, rapidly changing, like stars moving close to the speed of light, and the natural way to find that would be in a binary system. Most stars in the sky are in binaries. They're very stable systems. And so two stars that orbit each other in a binary system will produce gravitational fields that are constantly changing as the orbits around them are changing. This is another kind of embedding diagram, and in this case, the warpage of space around a massive object like a star is described as a peak rather than a dimple, but it's the same idea. Here's two stars orbiting each other, and the gravitational field felt by a distant observer is constantly changing. But the news of that constantly changing field is propagating outward through space-time with gravitational waves. They travel at the speed of light. Not because they have anything to do with light, but because it's the nature of space-time that the disturbances that cannot travel faster than that speed, the speed of light, corresponds to, if you like, the fact that the particle in the quantum language that carries that energy and information is massless. In the case of electromagnetic waves, the photon is massless. Electromagnetic waves travel at the speed of light, at least in a vacuum. In the case of gravity, gravitational waves are carried by a graviton. It'll be a long time before we observe gravitons, but gravitons are believed, at least in Einstein's theory, to be massless particles. They travel at that same speed. I like to say that light travels at the speed of gravitational waves. But I can't be sure because we've never directly observed gravitational waves, so that's one of the things we'll want to test early on. So that's sort of a little cartoon introduction to what gravitational waves are. You know that Einstein's theory has been tested many different ways, very, very precisely. Some of the classic tests are the bending of light from a distant star as it passes near the sun. In order to do this kind of a test, you need to wait for an eclipse so that you can see the star close to the sun. This was the classic experiment that made Einstein the first physics rock star, even before rock and roll. But another test, which has actually preceded Einstein's prediction, was the fact that Mercury's orbit is not a perfect Keplerian ellipse. It actually precesses. That precession was well measured even before Einstein, and he post-predicted the properties of that precession quite precisely. It was twice what people were able to calculate using some kind of Newtonian theory. And another classic test is more complex bending of light, known as gravitational lensing. And now strong gravitational lensing and even weak gravitational lensing has been observed in many, many cases. So these are classic theories, classic tests of general relativity, and general relativity has passed them all. But these tests have all been done in, if you like, the weak field approximation, where the curvature of space is relatively weak. And by contrast, general relativity has never really been precisely tested in the strong field regime. And in the strong field regime is where it gets interesting. And that's because in that regime, Einstein's equations that I showed you last time, g equals 8 pi t, are strongly nonlinear. And they're usually solvable in some linearized approximation. But in their full non-relativistic, full nonlinear glory, strong field gravity, or at least Einstein's version of it, is very, very hard to solve. And only recently have the most powerful supercomputers and the most clever techniques been used to even solve the two-body problem of gravity in curved spacetime. And of course, strongly curved spacetime and rapidly changing strongly curved spacetime really only happens in extreme regimes, the universe in the early moments of the Big Bang, and near or in the horizon of black holes. And those are sufficiently far away in time or in space that they don't affect us very much. So we didn't need to know general relativity until we started to care. But it is where general relativity gets very nonlinear and very interesting. And so to a physicist, this is the place to test. These are the best locations to test Einstein's theory. But we aren't close to these things, either in time or in space. So what we need is some kind of messenger that tells us how strong gravity behaves, how strong curvature behaves. And that messenger is a weak field version of what would be strongly curved spacetime, and that's what gravitational waves are. They're the messenger that tells us about strongly curved and rapidly changing gravitational waves far away from us. So part of the reason why we like to study gravitational waves and we want to observe them directly is to test Einstein's theory more precisely than ever before in regimes in which it has never been tested, in regimes in which it's the most interesting. Well, what does Einstein's theory predict about the nature of gravitational waves? This is my attempted PowerPoint animation. This is the best I can do. What a gravitational wave will do when it passes into the board is it will stretch and squeeze the space between objects, free-floating objects that respond only to gravity. Stretch and squeeze it in a wave-like manner, because gravitational waves travel in a wave-like manner. And this is called a strain, and it has it's a change in the distance between two objects divided by the distance between two objects. So it's a unitless quantity. And in fact, the strain, which is comes from the weak field linearized version of general relativity in the rapidly changing regime, is a unitless quantity. It's actually a tensor quantity, not a scalar quantity like this. It propagates, as I said, at the speed of light, according to Einstein's theory, and that corresponds in the quantum language to a graviton that is massless, in the same sense that the photon is massless for the electromagnetic radiation. And the distortions, the stretching and squeezing of space, happen transverse to the direction of propagation, just as they do for electromagnetic waves in a vacuum. But one difference between electromagnetic waves and gravitational waves is that electromagnetic waves do come in two polarizations, transverse to their direction of motion. The electric field is one direction or another direction, or some linear combination thereof. And you can fully describe electromagnetic fields propagating into the board in terms of a linear superposition of these two polarizations. And that's characteristic of dipole radiation, electromagnetic dipole radiation. But gravitational radiation cannot be produced by dipoles, because a dipole would require sort of a positive charge and a negative charge, and mass doesn't come in positive and negative varieties as far as we know, and so there's only positive, and the only way to get a dipole type radiation would be if they were moving back and forth like this, okay, but that doesn't conserve momentum. For an isolated system, that can't happen. So there is no dipole radiation, there's no monopole radiation, because mass doesn't just increase and decrease in isolation. So the lowest order multipole that can produce gravitational radiation is the quadrupole. And that corresponds to a pattern which is quadrupolar, which means that instead of the two polarizations being related by a 90-degree rotation, they're related by a 45-degree rotation. And in the quantum language, it corresponds to the graviton having a spin of 2 rather than 1. And so here's the two polarizations that you could define for a gravitational wave propagating it along the z direction, is that it would stretch space along the y direction, squeeze space along the x direction, and then a half a wavelength later it would do the reverse, and a half a wavelength later it would do the reverse. And the other polarization is rotated 45 degrees with respect to that. We call that cross polarization. So in Einstein's theory, there are two and only two polarizations. If you know remember your quantum mechanics, you know that a particle of spin 2 particle has 2s plus 1 or 5 polarization states, but not if it's massless. If it's massless, only the plus 2 and minus 2 polarizations, which linear combination of them are plus and cross, are available. Okay, so that's sort of a quick rundown of the properties of gravitational radiation as predicted by Einstein's theory. What about the sources? Again, the sources have to be quadrupolar. They can't be monopolar because that violates energy conservation. Can't be dipolar because that would violate momentum conservation. So you need some sort of quadrupole. And a dumbbell or a pair of orbiting stars is a beautiful quadrupole. Just like electromagnetism, the electric field that's generated in a dipole has to do with the dipole moment, the acceleration of the dipole moment, d double dot. And in the case of gravity, it's the quadrupole moment, I double dot, the acceleration of the quadrupole moment of a system of masses. And it's gravity, so it has to have Newton's constant in there somewhere. And it's a wave that propagates from some kind of quasi-point-like source out over the full volume of space. And so a wavefront falls off with an energy of 1 over r squared, or an amplitude of 1 over r. So just from dimensional analysis alone, you know that there's a g over here, there's an I double dot over here, there's a 1 over r. That doesn't give you a unitless strain. To get a unitless strain, well, you know, relativity is involved somewhere, so you need the speed of light. So you just throw in as many speeds of light, many powers of the speed of light as you need in order to get something dimensionless on this side. That's just dimensionless analysis. So up to a factor of 2, dimensional analysis alone tells you what the strain of a gravitational wave from a distant source at a distance of r might be if it's caused by an accelerating quadrupole moment. Now, if the accelerating quadrupole moment is just a pair of masses that are orbiting at some frequency f or some angular frequency omega, then I is just m r squared, where capital R is the distance between the objects. And double dot brings down 2 powers of 2 pi f, so there's a 4 pi squared f squared. And there's your expression for the amount of a gravitational radiation, the amplitude of a gravitational wave reaching the Earth at a distance little r away from the source, from 2 stars that are orbiting at a distance of capital R. Okay, so let's see how big that would be. Well, let's take these, the masses to be the mass of typical stars, like the sun, 10 to the 30 kilograms. Let's take a radius of 20 kilometers. That's a pretty small radius for 2 orbiting stars, I must say. But it does, by Kepler's law, give a frequency of 400 hertz, so 2 stars orbiting each other 400 times a second. That must be a pretty rare situation, so let's put it far away, because it's a big universe. Rare things happen somewhere in the universe, but probably far away. So let's put it a megaparsec away. This is a megaparsec. Which is about the distance to the Andromeda galaxy, nearest big galaxy or so. You put all these numbers into this formula, you get a strain of 10 to the minus 21. That's a change in length divided by a length, okay? And let's say you and I were about a meter apart, or 10 meters apart, or something like that. So a strain of 10 to the minus 21 means is that if we're a meter apart, the distance between us is changing by 10 to the minus 21 meters, which is a millionth of the diameter of a proton. Okay? So that's forget it, that's too hard to measure, okay? On the other hand, if we were separated by 4,000 meters, 4 kilometers, then a strain of 10 to the minus 21 corresponds to a change in the distance between us of only 10 to the minus 18 meters, or 1,000th of the diameter of a proton. That's easy. We know how to do that. We do that routinely. Okay, so so it's a very, very small effect, but it is measurable. Of course, I have to go back and ask myself, do we really expect stars to be orbiting each other 400 times a second? After all, how could 2 stars be separated by 20 kilometers when stars have a radius of about 1,000,000 kilometers? Okay, how are we going to manage that? Well, let's let those stars go supernova. Their cores, which have burned hydrogen into helium and helium into oxygen, carbon, oxygen, and nitrogen all the way up to iron. And you really can't burn iron. Iron is the most stable nucleus. By the way, I use the word burn in the loose sense of the word. This is normal chemical burning. This is nuclear burning. But you can't really release energy by fusing iron, so it stops there. And when it stops there, then you've got a degenerate core. You've got a very dense core of iron, and that core of iron eventually, if the star is massive enough, just can't withstand the gravitational pressure from above, and the whole thing collapses. And the way it does it is by, well, you know, the protons will sit there and eat up the electrons and turn into neutrons. The electrons will be gone, neutrinos will be emitted, the neutrinos will escape, and now there's no longer any electrons, no longer any atoms, and the whole thing collapses into a single nucleus of neutrons, and that's a neutron star. It produces a gigantic shock wave which propagates outward, blasts the outer layers. That's a supernova. All that material that gets blasted out in the supernova would probably collect to form second-generation stars like our sun and people and stuff like that. Okay, so that's where our carbon and oxygen and nitrogen comes from supernovas, things like that. Yeah?
Could you give us the logic again, because you pulled stuff out of the hat to end up with 10 to the minus 21.
I pulled some numbers out of the hat, that's
yeah,
right. All for good reasons, by the way.
I know, but can you sort of explain the logic
yeah.
a little bit?
If these were ordinary stars.
Is that right?
That's right. If these were ordinary stars, and you know most stars are binaries, right? So ordinary stars are typically orbiting each other once a day, let's say. I don't know, in Tatooine, how long did it take? I don't know. But you know, a day, hours, something like that. That produces gravitational waves. They're pretty weak because it's very non-relativistic, but also they're low frequency. How low? Well, you know, 1 in 8 hours. Well, 1 in 8 hours means that we're going to be looking for stretching and squeezing of space that's very slow.
Because you have that squared, you want as high an F as possible.
That's step one. That's logic point one.
Right.
Logic
the other has to do with R.
No.
No.
The other part of the logic is that low-frequency gravitational waves are hard to detect because the Earth is vibrating like crazy at a hertz and below. In fact, the Earth is really vibrating at about a sixth of a hertz. You know why, right? Sixth of a hertz. If you really, seismometers, geophysicists all know this. A sixth of a hertz. Why?
Sound crossing time.
No.
Time.
Well, maybe it's related to that. When was the last time you were at the beach and counted the waves coming in? Somehow the oceans are sloshing. Somehow. We know the oceans slosh. The waves come in about once every 6 seconds. Count. You'll see. That's called a microseismic. The waves crashing on the ocean, on the continental plates, are causing the continents to vibrate at about a sixth of a hertz. There's no way we're going to detect gravitational waves at a sixth of a hertz on the ground. You can do it in space, but not on the ground. But the detectors that we're building on the ground really are no good below about 10 or 20 hertz. That's why I need a big number here. That's why I need a really small number here. That's why I can't use ordinary stars. I must use compact neutron stars orbiting each other. You might argue, wow, that sounds exotic and rare. Yeah, I'm a physicist. I love exotic and rare. Okay, number one, and I can tell you why. Neutron stars are the coolest things in the universe, amongst the coolest things in the universe. But also because, because they produce gravitational waves that we can detect on Earth. That's the logic that I'm trying to get to. And I was going to say all that, I promise you. So let me just go on. So the point is that neutron stars are pretty exotic, and neutron star binaries are even more exotic, but they do occur, and I'll tell you about them. There's about half a dozen of them that are known in our galaxy, and they're producing gravitational waves, and we actually know that. But we've never detected them because they're orbiting at periods that are too low for us to detect the gravitational waves in. But another lesson that you can learn here is that if you play with these numbers, or if you play with this formula, you'll find that anything that you can do on Earth to detect gravitational waves, to produce detectable gravitational waves, is going to fail. Because this strain will be too small. What you'd really like to do is what Hertz did, 150 years ago. After Maxwell told him that electromagnetic radiation is caused by, accelerating electrons, well, he just built a little spark machine over here, and then he built a little radio. Well, he had to invent the radio. He invented the radio and he put it over here on the other side of his laboratory and detected the radiation from there to here. Okay? Because after all, that electromagnetic radiation was at terahertz frequencies, so he's in the far field already over here. Okay? And we can't do that on Earth. There's no way that we'll be able to build a source on Earth that produces gravitational waves, even with R's of 1 meter. 10 to the 23 we got to gain. But it's hard to gain on this m of 10 to the 30 in the numerator. It's really, you need stars in order to produce gravitational waves big enough. And they have to be compact stars, like neutron stars and black holes, to produce high enough frequencies, to produce large enough strains, and to produce them at frequencies that are detectable on Earth. So that's the logic. Okay, and we do know about a handful of such sources. This is the first and most famous one, the Hulse-Taylor binary. The Hulse-Taylor binary has a pulsar, which is a neutron star, and it's sending out a beam of radio waves. And as it spins on its axis 17 times a second, imagine a star spinning on its axis 17 times a second. I mean, this is a star. It has the mass of the sun, but it has the size of New York, and it is spinning around on its axis 17 times a second. And that pulse, that beam hits the Earth 17 times a second, producing a pulse. And that pulse was observed by Hulse and Taylor, or Weisberg and Taylor actually, a long time ago, in 1975. And they noticed that it was a fantastically good clock. So they compared it to their atomic clocks. And when they compared it to their atomic clocks, they found it wasn't so good. It actually had a sinusoidal variation, but with an 8-hour period. Perfect sinusoid with an 8-hour period. So obviously, what's happening is that this spinning neutron star, this pulsar, is orbiting another star with an 8-hour period that's kicking it around. Well, Doppler shifting it a little bit earlier, a little bit later, and that was what they were observing. So they've discovered the first compact binary system. Okay, it's in our galaxy about 7 kiloparsecs away, not quite to the center of the galaxy. And they thought that was cool. So they decided to measure it and continue to measure it for 25 years. And over 25 years, they found that this 8-hour period was shrinking. And they plotted the loss of perihelion, cumulative shift of the periastron time in seconds. And they found that the periastron lost 35 seconds in 30 years. Okay, not very much, but it did form this lovely, that's the data points, by the way. And then they just said, well, I don't know what's causing this decay of their of the orbit, but if it was caused by gravitational radiation, then here's what we would observe, and that's the line over there. And that line is not a fit to the data. That line is just a prediction that the energy is lost by gravitational waves. And I must say, it convinces me, this system is losing energy by gravitational radiation. Energy and angular momentum, causing the orbit to shrink. And in about 300 million years, these two stars are going to smash into each other. I'm not going to wait around that long. But there are a bunch of these systems in our galaxy that we've observed now. And pretty much one of these systems will merge and smash into each other every 100,000 years. So all we need to do is look at about 1 million galaxies, and we'll see about 10 of these per year. Okay? Just look at a million of these galaxies, we've got to look far enough out. Okay, about 100 megaparsecs. Yeah?
Isn't that one of the outstanding questions in terms of physics models, how many such merging neutron star systems we have?
Yeah, because in our galaxy, we've got about 6 or 7. Actually, one of them is going to merge in more than a Hubble time, more than 13 billion years, so don't even count that one. And so because there's only a handful, extrapolation is a dangerous thing to do. And therefore, the error, as they say in astronomy, is in the exponent. And so what we figure is that we will see gravitational waves from one of these systems with our advanced detectors that I'm about to describe, maybe once a week, maybe once a month, maybe once a day. In other words, a factor of 10 uncertainty. Okay? But we hope at least once a year. Well, not just hope. There's a 99% chance that we'll see one a year at design sensitivity of our detectors, which we hope will be 2016, 2017. Okay? Does that answer? So in any case, this is pretty convincing indirect proof that we didn't see the gravitational waves. We don't see the gravitational waves from these things. There's no stretching and squeezing of space that we've been able to measure. We just know that energy and angular momentum is lost from the system. So we want to look for these things to study the waves, to study the sources. They're very interesting, energetic things. By the way, when neutron stars smash into each other, things get really interesting, as I'll talk about later. But another reason, maybe a more general reason why it's interesting to look for gravitational waves is that they really are a new way of looking at the universe. You know that the history of astronomy has been punctuated by major revolutions caused by opening up new bands in the electromagnetic spectrum. For thousands of years, astronomy was looking at light, visible light from do you have anything that's better than this? From stars. But when we started to look in the infrared, that requires space telescopes, or telescopes above most of the atmosphere, we saw the births of stars and hot gases forming stars. We started to learn about star formation. When we looked in the microwaves, we saw the light from the Big Bang. When we look with X-rays, we see, pulsars, because they emit energy not just in radio, but also in X-rays and gamma rays. And also interesting compact binary systems, like matter falling into black holes, producing X-rays and gamma rays. The universe looks entirely different in different bands. But gravitational waves are not just another band of the electromagnetic spectrum. They're a whole other spectrum. They're a whole other form of radiation. Electromagnetic waves are produced more or less by the incoherent motion of electrons in atoms. Gravitational waves are produced largely by the coherent motion of large amounts of mass of any and all kinds, including dark matter and anything else. As long as it moves fast enough, it'll produce gravitational waves that are loud enough for us to potentially detect. So gravitational waves are very different, and they carry very different information than light or electromagnetic waves. They're really a totally new and unique window on the universe, and we don't know what we're going to find when we start detecting gravitational waves from astrophysical sources, because they may be from things that we've never detected before because they don't emit light. Like orbiting black holes smashing into each other. Wouldn't it be cool to find that? Okay, so that's sort of the motivations. And the kinds of sources, astrophysical sources, that we're interested in looking for are, varied. As varied as, and these are the things we can think about. They're varied. So there's, for example, the things that I mentioned earlier, binary systems, binary neutron stars or binary black holes, compact objects in binaries that are, have accelerating quadrupole.
What is compact?
It means smaller than ordinary stars. So neutron stars and black holes, when they orbit each other, they can do it really slowly if they're very far apart. But they could also, after a while, spiral in and get really close. Ordinary stars can't get close. They're too big, right? So compact means it has to be really small, because then the distance between them can be as small as tens of kilometers, which means by Kepler's laws, the frequencies can be as large as 10, 100 hertz, audio band, by the way. So you can hear these things, and eventually we will. And those are the things we can detect on the Earth. So compact means neutron stars and black holes, or things that we haven't thought of. Like strange stars, well, we've thought of those, but we don't know what they are. They're strange. They're made up of strange quarks, so they're very compact because strange quarks reduce the quantum degeneracy pressure of these objects. These are all degenerate matter, really interesting stuff. Actually, black holes aren't even matter, although they are mass. Spinning neutron stars just by themselves might produce gravitational waves, but only if they have an accelerating quadrupole moment, and a perfectly spherical neutron star has no accelerating quadrupole moment, because as it spins, it's no different than if it didn't spin. But if it has a little mountain on it, a centimeter or so, on a 10-kilometer radius neutron star, maybe because it's got some crust of iron that is cracked, maybe because of a star quake, all kinds of things could produce an accelerating quadrupole for a single lone spinning neutron star. And there are hundreds of millions of neutron stars in our galaxy. Let's hope this works better. Yes, the red kind. Okay. So that's another potential source. That would produce just a sine wave. Just a sine wave. Not quite just a sine wave, because after all, we're moving with respect to it in a well-known way. Exploding stars. Remember that a very massive star will burn its core to iron, and after that it just can't burn anymore, and if there's enough mass, it'll eventually, the core will collapse, the outer layers will get shocked out and produce a gigantic explosion, a supernova. Those happen about 3 times a century in our galaxy. We observe them routinely in distant galaxies, core collapse supernovas, and they will produce gravitational waves. They're not there's some asymmetry there, but not a lot. We don't really understand core collapse supernovas very well. It's likely that we would never detect gravitational waves from a core collapse supernova outside of our galaxy. They have to be inside. And like I said, a core collapse supernova in our galaxy 2-3 times a year, most. A century, most. So it's, you have to wait. Gravitational waves were also produced in the roiling conditions of the Big Bang, the earliest moments of the Big Bang. This picture is of the cosmic microwave radiation, which was released when the Big Bang had cooled enough for the first atoms to form. And so the plasma that scattered the light was gone. It just became neutral matter, hydrogen. And all that light then flowed freely from then on, and that's the cosmic microwave background that we see today. It was emitted about 370,000 years after the Big Bang. Gravitational waves have been free-flowing since about the Planck time, 10 to the minus 43 seconds after the Big Bang. So people talk about the CMB as the baby picture of the universe, and indeed it is. But gravitational waves from the Big Bang, if we could ever see them, and it's a long shot, are like, just came out of the womb, snap that picture. I mean, really, the Planck time, or if not the Planck time, it depends on the details of inflation or whether inflation existed, but maybe let's say 10 to the minus 22 seconds after the Big Bang. Really, really early on. So there are lots of interesting sources. They're not all realistic to be detected in our next generation of detectors that'll come online in the next couple of years. This one might be a real long shot. This one, well, you could argue about every one of these things, okay? But we're pretty sure that we'll be detecting these. Okay, so let me switch gears. I'll return to the sources if I have time at the end, but I wanted to take some time to talk a little bit about the detectors, because the ability to detect stretching and squeezing of space to a part in 10 to the 21 or 10 to the 22 it's just not easy, and our detectors are carefully designed and carefully engineered, and the advanced LIGO detectors that are being built right now have not yet been made to work. We don't know if we can really get to 10 to the minus 23, which is what we're trying to get to, but let me just tell you a little bit about how they work, or how at least we intend for them to work. Okay, actually, and I should remind you that the initial LIGO detectors were built in the year 2000, and they operated from about 2000 to 2010. And they were very sensitive. They could detect strains on the order of 10 to the minus 21 or a fraction of 10 to the minus 21 in a frequency band around 100 hertz, like between 50 and a few hundred hertz. Okay? No ability to detect strains, such low strains at lower frequencies. It's too much motion. But those detectors did not detect any gravitational waves. They were not sensitive enough. There was too much noise in the detectors. And I'll tell you a little bit about that. Okay? So the advanced LIGO detectors are designed to reduce the noise by a factor of 10. If the noise is reduced by a factor of 10, it means you can detect a source 10 times further away, which means you can detect a source in a volume of space 1,000 times bigger. So if in the initial LIGO detectors we were hoping to detect one binary neutron star merger in 10 years, and we operated for roughly 10 years and didn't see any, but on the order of 10 years, 1 in 10 years, the advanced LIGO detectors will see 100 in a year. Okay? So that's the calculus. It's as simple as that. The detectors are Michelson interferometers, which is a lovely, full circle, because it was the Michelson experiment that convinced Einstein that there was something to his notion of special relativity. Then he generalized the general relativity, and now we're trying to do unique tests of general relativity with a Michelson interferometer. So the idea works very simply. The laser comes over here, goes to a beam splitter, half the light goes through and comes back, the other half bounces and comes back, it recombines at the beam splitter. You can arrange things, typically in a Michelson you do arrange things such that the interference is completely destructive out what we call the dark port, and completely constructive back to the laser. So all the light comes back to the laser, and the dark port remains dark. Then, if a gravitational wave comes into the board, it stretches space in this direction, changing this length, and in the 90 degrees away, it squeezes space. So now there's an unequal lengths, and now the interference pattern is ever so slightly different. A little bit of light comes out of here. That's our signal. Okay? And since a Michelson detector detects changes in length, and we want to measure very, very, very small strains, we need very, very, very large lengths. And the length of our Michelson interferometers is 4 kilometers. It's a 4-kilometer vacuum tube. And it's a little bit more complicated than all this, but I'm trying to make it as simple as I can. These detectors are not really like typical telescopes. A telescope, you point, and you look for light coming from there, and you don't see any light coming from somewhere else. And we're not going to point these things. They're way too big. Okay? These are more like antennas. So you know how dipole antennas work. You know, you have a metal rod like this, and then electrons are going back and forth inside the rod against the ions that form the metal. So charge is conserved, and you get a little dipole pattern. And such a dipole antenna has a dipole pattern of emission of light if you use it as a transmitter, or absorption of radiation if you use it as a receiver, like a dipole antenna on a 20th century television, something like that. The pattern is such that it's more sensitive to radiation coming this way than coming from this way. There's a dipole pattern, antenna pattern associated with it. Gravitational waves have to be detected with a quadrupole antenna. So instead of the two arms of being dipolar, it's quadrupole, like this, 90 degrees apart. So here are the two arms of our Michelson interferometer over here, and this shape here is the response of the detector to gravitational waves of plus polarization as a function of the direction in which they come. So if they come from directly overhead, plus polarization aligned with the arms, then the response of the detector is maximum. If it comes 45 degrees, there's a null. It stretches and squeezes both arms at the same. There's no change to the Michelson pattern here. So there's a null. There's no response here. And in between, it's sort of in between. And that's for plus polarization. It's even more complicated for cross polarization. And for sort of mixture of polarizations or circular polarization, you get what we call this peanut pattern. And what this pattern is telling you is that you can detect waves from pretty much all directions. There are some directions that you can't, but pretty much all directions. It's not a 4 pi detector. It's more like a 2 or 3 pi detector. But in any case, it's not heavily directional. You don't have to point. The flip side is that if you detect a gravitational wave, you have no idea what direction it came from. No idea at all from a single detector. So what do? Well, you do what radio astronomers know how to do. You build an array of these detectors, a phased array of these detectors, and you use triangulation, coherent triangulation of the wavefronts to locate the source in the sky if you want to do astronomy. So we need a network of detectors to do this. Okay? Let me skip this one. Here's our network of detectors that are being built right now. These are all second generation detectors. They all had initial versions. The LIGO detectors are Laser Interferometer Gravitational Wave Observatory, and they're built by Caltech and MIT for the National Science Foundation. And we have two sites, one in southern Louisiana called in Livingston, Louisiana. And here's our 4-kilometer long detector arms, Michelson arms, and one in eastern Washington State in the Hanford Nuclear Reservation operated by the Department of Energy. So we have two sites for LIGO detectors. Our friends in Italy, in collaboration with the French, have built the Virgo detector outside of Pisa, Italy. Our friends in Japan are building the KAGRA detector inside the same mountain that the Super Kamiokande detector, if you know what that is. It's underground, and it's being built right now. I think the tunnels are almost finished. And there's a smaller detector in Germany called GEO. It's only 600 meters. This is 5-kilometer arms. These are 4-kilometer arms. This is a 3-kilometer arm. And then actually the LIGO laboratory actually built 3 detectors. And the plan was to put 1 in Livingston and 2 in Hanford. That's what we did for the initial detectors actually, but 2 in Livingston. But then we thought, maybe it's better to have another detector someplace far away so that the triangulation and locating source in the sky works a lot better. And of course, what you'd really like it is in the southern hemisphere. Wouldn't it be great? We even have a site in Perth, Australia, called Gingin. But we needed to make the site real, and that was going to cost $100 million. So we asked the Australian government, could you come up with $100 million? And they said, oh, sure. And then they had an election. And then they changed their mind. And so no money from Australia. And just about then, the economy was somehow booming for some subset of India. And so the Indians said, we'll do it. So we built a third advanced LIGO detector, and it's now in crates, waiting to be shipped to India. We don't have a site yet, but we hope to soon. So by 2018, 2020, there will be a LIGO detector in India. Yeah.
How are these different than for you?
All differently. The initial LIGO detectors were designed to have, and the advanced LIGO detectors as well, they use the same vacuum system, were designed to be oriented as closely as possible to be the same, so that they were detecting the same polarization of the waves, because if they weren't, then one detector would see something and another detector wouldn't see something, and that's bad. You really want simultaneous detection to convince yourself that you're seeing something extraterrestrial. Otherwise, it's just noise. How do you convince yourself fully that it's not some local disturbance? So you wanted them to be aligned. The other guys, well, the Earth is round, and you just can't align them all the same anyway. But by this time, we realized better to just mix and match. Because if you mix and match, then you're sensitive to different polarizations, and that's really important. If you can detect the different plus and cross polarizations, if you can disentangle them, plus polarization, well, actually, a face-on orbit gives you the strongest signal, and it's circularly polarized, plus and cross in equal measures. An edge-on signal has the weakest signal, and it gives you just linear polarization, just plus or just cross. And what you need is to know which, because you want to know from the loudness of the signal how far away it is. Because these sources are standard candles, and you could do cosmology with them. And that's what we'd like to do. So we want to disentangle the polarizations, which means we need our detectors to be oriented just in totally different ways. Okay. And triangulation. You know, the thing about triangulation and coherent, like a phase array of antennas to locate sources in the sky is going to be limited by the usual thing that limits astronomical accuracy, and that is, you know, your aperture and your wavelength. Okay? Diffraction limited observation is limited by your wavelength, and the longer the wavelength, the more the diffraction, and the less well you can locate a source in the sky. So if you're using optical light, an optical telescope can locate sources in the sky to a 60th of a 60th of a degree, or even smaller. Okay? For us, we'll be lucky to get a degree, because our wavelengths are associated with are hundreds of thousands of kilometers, and they're associated with frequencies in the audio band, not in the terahertz band, in the audio band. So we will never be able to locate sources in the sky very well. But we really do want to locate sources in the sky, because some sources will be not only sources of gravitational waves, but also of light. And here's a scenario that we think will play out. The idea is this. Here's an orbiting pair of neutron stars. Okay? And they are they're emitting gravitational waves, and they're about to merge. They're about to coalesce. We will detect these things, we hope, from about a few minutes before the coalescence to the moment of coalescence when they smash together. That's when the gravitational waves are actually loudest, because the frequencies are highest, the amplitude of the wave is the largest. Okay? And then, as they smash into each other, they make a gigantic mess. And that gigantic mess produces a huge burst of light. And if that light is focused in beams and relativistically boosted, it produces jets of gamma rays. And this happens, these are called gamma ray bursts. In fact, we detect gamma ray bursts with gamma ray telescopes on the order of once a day. And fortunately, gamma ray telescopes can see a large fraction of the sky. So all they got to do is just look out there. Ah, there's a bright spot. Ah, there's a bright spot. They last for seconds, maybe 100 seconds. Usually it's often less than 2 seconds. Okay? Gamma ray bursts are really interesting and mysterious things. They're beamed. We will detect the signal before the gamma ray burst. So what we'd love to do is tell everybody, point there. Well, a gamma ray burst happens within 2 or 3 or 10 seconds of the coalescence. We just don't know how to be that fast. But we think we can tell people where to point within about a minute or 2. In fact, we know we can. A minute or 2 after we detect the signal, we can tell optical telescopes to point in that direction and see, you probably missed the gamma rays, but after all, you're optical telescopes anyway, you're not going to see the gamma rays. But look for some afterglow, maybe an X-ray or a radio or optical or afterglow caused by all this material being spewed out into the interstellar medium and causing and emitting ordinary optical light. Okay? And that is an afterglow that might last tens or hundreds of seconds. There's a longer scale afterglow, which comes from the interstellar medium, which is usually associated with radioactivity and so on. That can last for days. And then the radio emission could last for actually months, actually. So what we'd like to do is detect these events, and within seconds or within 2 minutes, tell telescopes where to point. So what we did was we sent out a call to all you optical astronomers out there who have robotic telescopes that can, wide field robotic telescopes that can point to look for optical transients, which are hard to find. Let's face it, optical transients are tough to find. So we put out a call, and virtually everyone in the optical transient business answered our call. 64 different groups around the world said, we want to look, tell us where to point. So far we haven't seen anything, because we haven't finished completing our detectors. But the idea is that when this does happen, and we start detecting, then all the optical transient astronomers in the world will find, if there is, some kind of an optical afterglow. And then we'll be in the regime of multi-messenger astronomy. Gravitational waves, potentially gamma rays, potentially optical and radio, lots of different messengers. The more different messengers carrying information about a source, the better you will understand the physics of that source, the physics and astrophysics of that source. All right, a little bit more about the detectors. I've talked for an hour. Gotten through a few slides. I've talked for an hour, so I have to wind up. But I wanted to show you a video. Now, this is embarrassing. I'm going to have to whiz through about 40 slides to get to my video. Okay, I'm sorry, I'm embarrassed by it, but I'm going to do that. I'm going to whiz through. Here's our detectors, and here's all the people who work on the detectors, not even the people. Here's the LIGO Livingston detector, and here's the beam tubes. They were built 10 years ago, 15 years ago now. One of the largest high vacuum systems in the world. Here are the chambers that house our mirrors for our Michelson interferometer. Here are the seismic isolation systems, the initial seismic isolation systems. Here's what one of our mirrors looks like. You can see right through it with visible light. But with laser infrared light, they're 99.999% reflective. And they're hung like a pendulum with a wire that's too thin to even see. And lots of disasters. We at least covered the darn beam tubes with concrete bunkers. But there have been earthquakes, fires, more fires, locusts, floods, boils probably, all kinds of things. I got to whiz through all my slides. I got to talk about noise. Wanted to talk about how we approached sensitivity. I want to show this slide. I'm embarrassed that
Take another 10.
yeah, okay. But anyway, the initial LIGO runs lasted till about 2010. And this is our dark period now. It's about to end. Well, sorry, this is wrong. It'll be up here. It's going to end at the beginning of 2015 when our advanced LIGO detectors will come online. But what I didn't really show you was that it took 5 years, from 2000 to 2005, for our initial detectors to reach design sensitivity. We still never detected gravitational waves, but at least we made detectors that were sensitive enough that what we promised the National Science Foundation, we delivered. Okay? And that's why they gave us an additional $200 million to build the advanced detectors. You have to build up confidence by actually showing that you can build detectors that can detect strains on the order of 10 to the minus 21 or even 10 to the minus 22 before they'll let you build something that you think will work at 10 to the minus 23. And that's what we're building. And we don't know whether it's going to take 1 year or 2 years or 3 years. If it takes 2 years, well, we'll be detecting gravitational waves in the centennial of their prediction by Albert Einstein, who, by the way, never thought that they would ever be discovered. But it might take a year or two after that. So just to manage expectations. You'll read about it in the New York Times, but it might not be till 2018. To get there, we have to improve our sensitivity. These are our sensitivity curves. This is strains of 10 to the minus 22, and this is 100 hertz, and this is 1,000 hertz. And the initial LIGO detectors couldn't detect anything below about 50 hertz, and the advanced LIGO detectors are going to want to try to go way down to 20 or 10 hertz, where binaries spend a lot of time. We can get a lot of signal from this time. And then the merger happens out here at 1,000 hertz.
What are the resonances on your sensitivity?
The resonances are 60 hertz due to the electronics. Love to get rid of that. This, and all the multiples of 60 hertz. 60, this is 60, 120, 180. You can see already that it's a square wave, not a sine wave. 300 and so on. This is 340 hertz. This is the mirror hanging from a pendulum, and the pendulum swings at about 1 hertz, and we can control it at 1 hertz. And the wires holding up the mirrors are vibrating at violin modes. 340 hertz, multiple. All of these are the violin modes of our suspensions. This one is a calibration line. This one is a calibration line. These are actually the body modes of our mirrors shaking internally because of thermal excitation, because they're 290 degrees above absolute zero, and they're shaking at 5 kilohertz. We don't expect a whole lot of astrophysical sources at 5 kilohertz, but if they are, I hope they're broadband because we ain't going to see them at exactly that frequency. Okay?
When you say calibration line, you have a...
Oh yeah, we shake the mirrors. We shake the mirrors at exactly 1 frequency. Well, 2 or 3. We have 2 or 3 calibration lines. Otherwise, how would you know what our response is? It's not easy to calibrate the LIGO detectors. We can shake them at levels of 10 to the minus 18 meters amplitude. Okay. They're made up of atoms, which have dimensions of 10 to the minus 10 meters. So it's not an easy thing to do, but we can do it. And for advanced LIGO, we just have to push in all these directions. Better seismic isolation, better test masses and suspensions, higher powered lasers and thermal compensation to improve the sensitivity. And that's a lot of fancy equipment, let me tell you. This is a 200 watt infrared laser. Not many people have lasers that powerful. They're built specially for us. This is a mirror that's 40 kilograms, made of fused silica. It has a quality factor of 10 to the 8th. It's hanging from another one, which is hanging from a piece of metal, which is hanging from another piece of metal. This is a quadruple pendulum. It's not a simple thing either. The seismic isolation systems are active now instead of passive, and they're very sophisticated. I need to wind up. But I am going to warn you that advanced LIGO isn't the end of the game, because it never is. Even if we did in physics. Physics, you always want to do better. The advanced LIGO detectors will hopefully detect lots of gravitational waves. But we'll want more. We don't want 40 detections a year. We want 40 detections a minute. How do you get that? Build third generation detectors. They're on the drawing board. It'll probably take 20 years of development to get them there. You better start now. That's how it is in frontiers of physics. One way to do better is to take the quantum noise associated with our laser and manipulate it. Actually, not even associated with our laser, associated with just the vacuum. There's quantum noise associated with the vacuum, and that's what limits us. But we can fix that. we can squeeze the quantum vacuum using quantum electro-optics. And this is also really fun. It's a teaser. I don't have any time to talk to you about it. I wanted to show you a video of what one of these explosions looks like. This is just a cartoon. It's an artist. Oops. It's an artist's conception of two. It's just a cartoon. It's just an artist's conception. Okay. Two neutron stars orbiting each other. They're now emitting a lot of gravitational waves. They're tearing each other apart, and they're producing a gigantic burst of energy, which is beamed. That's a gamma ray burst that you can see from across the universe. But before that come the gravitational waves. I wanted to show you that one, but that's really a lead up because that's just a cartoon. Let's get more real. We're physicists. I can't show you a video of something real, but I can show you a video of a more or less exact solution to Einstein's equations. You guys, you all know how to solve the two-body problem. You learned that in Physics 1, right? Not in the presence of gravitational waves. The two-body problem in general relativity is one of the outstanding problems. But it was solved a few years ago using supercomputers and a lot of clever ideas. And here is one such solution. The most accurate. Here's two black holes. Now this is a supercomputer simulation. It's not real, okay? But it is a more or less exact solution to Einstein's equations in the nonlinear, strong field, very, very relativistic regime. You can see the orbiting black holes. You can see the curvature of space below. You can see the arrows. That's the time lapse. That's time falling into the black hole, if you like. And here's the gravitational waveform. And it's a chirp. It goes low frequency, low amplitude. But as the black holes orbit each other, they're emitting no light, by the way. These are black holes. There's no light emitted. But as they approach each other, the black holes get sufficiently close that there's no longer any way to distinguish them as being two black holes. They start to kiss right about here, and their horizons merge, and they merge into a single black hole, which then rings down like any kind of an object might ring down after it's been excited. Let's skip that one. And the point, this is two black holes kissing, so you might want to see that. I don't know. Depends on what you're interested in. But this is what people who study relativity want to see. And they can see it on their supercomputers, but it's just solutions to an equation. We will see it from astrophysical sources and then compare. And in order to compare, and when we compare, we will make really unique and powerful tests of general relativity in the strong field regime. Will general relativity fail? We know that general relativity is wrong ultimately because it's not even quantum mechanical. Okay? Where does that failure occur? Will it occur with these astrophysical systems? Probably not. But if it does, well then, I hope that the LIGO effort will produce not one Nobel Prize, but two. So that's one of the promises of the field. We look forward to the coming advanced detector era, the discovery and exploration of the gravitational wave sky, unique tests of general relativity in the strong field, highly nonlinear and dynamical regime, joint observations and discoveries with electromagnetic and neutrino telescopes, and opening up a whole new branch of astrophysics. That's what we look forward to because we can anticipate it. But as you know, in the discovery world, what's really interesting is what you don't anticipate. And that is what I look forward to the most. Thanks very much.
All right, thanks for that great talk. So yeah, we definitely have some time for some questions.
Yes.
So what are you detecting today at your current sensitivity? You're not detecting any astrophysics, but maybe something interesting on Earth, like whatever military exercises in China.
So gravitational. Right now we're down because we're just about finished installing our new detectors, which took 3 years. We're starting to commission them. So we are operating the detectors in some limited way. But 3 or 4 years ago, we were operating the initial, or what we call the enhanced LIGO detectors, routinely. So what were we detecting? We think it was all just local detector noise, but certainly earthquakes anywhere in the, on the Earth were detectable. Our detectors are designed to be as insensitive to the environment as possible. So it's a pretty darn expensive seismometer. We are not looking for things on the Earth. However, there is a unique kind of a signal that we could detect at low frequencies. Two kinds that are hard to detect any other way. One is Newtonian gravity. A large weather storm comes through and produces a lot of matter transfer, mass accelerations. We can detect those, but they tend to be low frequency. We would in principle be able to detect Newtonian rapidly changing gravity. And that's kind of unique, all right? And that can't be shielded. We can't shield gravity. We can only shield mechanical seismic motion, okay? So we try to be as insensitive as possible to seismic motion, but Newtonian gravity rapidly changing, like a weather front or something, we could detect. Another kind of unique and interesting thing is that we have two detectors separated by 3,000 kilometers because we don't want environmental influences to affect both of them at the same time. And most environmental influences happen at the speed of sound. And that's, long time, for gravitational waves, they'll hit the two detectors even if they're coming just from this direction. It's 10 milliseconds to get from one detector to another at the speed of light. So really, we're looking for coincidence. But if you have a lightning strike halfway in between, then they could hit both detectors. All right, that's very improbable. But here's something that happens. Lightning strikes anywhere in the world, and it excites Schumann resonances. Anybody? Schumann resonances. Schumann resonances are resonances of the cavity between the Earth's surface and the ionosphere. They're electrical resonances in the atmosphere up to the ionosphere, which forms a cavity. And they resonate at 8 hertz and 16 hertz and 24 hertz, that kind of a thing. And they are global. They'll produce electromagnetic storms all over the globe almost simultaneously. And our mirrors are hanging like pendula, and they're made out of fused silica, so they're not magnetic. But they're hanging from but you have to push on them. We need a way to push on them. And for the initial LIGO detectors, the way we pushed on them was we glued tiny little magnets to their back, and then surrounded them with coils so that we can magnetically push on our mirrors. Now, in Advanced LIGO, we're not doing that, but they're hanging from another mirror, which does have magnets glued to it. So an electromagnetic pulse, a global one, will move our mirrors, and our detectors will detect it. Now, will we detect seismic disturbances or nuclear tests in India? Yes, but our seismometers will do it much better than our detectors will.
In the simulation you showed of these black holes, you can estimate where quantum states would come in. You were just saying, well, maybe those estimates are wrong. But it's at the very, very end. Where is it?
Okay, so of course, we don't have a quantum theory of gravity, but we do have an approximate quantum theory of gravity. We are pretty confident, at least with our modern understanding of gravity and quantum mechanics, that black holes are as classical as they can be, except inside. Inside. Now, when these black holes merge into one black hole, you might think that you're exciting their internal degrees of freedom. And those internal degrees of freedom are probably what's responsible for giving black holes entropy, and therefore Hawking radiation. And although we've never observed Hawking radiation, we're all convinced that it exists. And there must be some substructure inside of black holes, and maybe the merger of black holes could excite them. Now, the only theory that I know of that can attempt to do this is string theory. And string theory has actually succeeded in doing this. String theory predicts a microscopic structure of black holes in quantitative agreement with Hawking's prediction, with Hawking's classical description of the entropy of black holes. That's a no mean achievement. In fact, to a string theorist, it's proof that string theory is right. I mean, I'm exaggerating only slightly, but probably a string theory theorist wouldn't exaggerate. They'd say that and believe it, because they understand it better.
So all of that is happening in terms of your movie.
Imperceptible. A string theorist would say that stringy internal structure of black holes cannot, in the scale that they understand it, cannot be excited through black hole mergers, at least not stellar mass black hole mergers. On the other hand, the neutron star mergers are awesome, because neutron star mergers produce gigantic splashes of materials out there. It's a unique probe of nuclear physics in a very, very dense regime that cannot be probed on Earth. It's also a unique probe of gravitational fields that are stronger than anything that could possibly be probed on Earth, and even electromagnetic fields and weak fields, because neutron stars are actually in weak beta equilibrium. The weak interaction is very strong inside of a neutron star. Remember, I told you that neutron stars come from the collapse of massive stars, and the outer layers are spewed out, producing all the heavy elements that make up you and I. But it doesn't really work quantitatively for the elements heavier than iron. For elements heavier than iron, supernovas can't explain it, core collapse supernovas. Gold, uranium, supernovas can't explain it. Neutron star mergers. Neutron stars are the dead remnant of a massive star, but it's not their last death. If they're in a binary, then when they orbit each other, they'll smash together in a second death, even more spectacular than the first, releasing even more energy and even more very massive neutron-rich material. You and I are stardust, but my ring is probably neutron stardust. And the way to really understand this well is to see the gravitational waves from them. We're hoping to do that.
Okay, maybe one more question.
Coming back to this understanding there will be some quantum effects from the last period of the merger takes probably like few short times, right?
Right, which we're talking milliseconds.
Right, and then then it's incredibly unlikely that you can test any quantum substructure.
That's what our string theorist friends who try to understand quantum substructure tell us. And that's because really with those time scales, you're talking distance scales, light travel distances on the order of kilometers. And what you're trying to do is probe the stringy singularity, it's not a singularity because string theory cuts it off, on distance scales of Planck scale.
No, I mean different things. No. Quantum substructure could be, we should not confuse the short distance quantum structure and long distance quantum structure.
I can already tell you know more about this than I do.
Right.
So go on.
No, I'm talking about, of course, Planck scale structure you cannot probe this because that's obvious. But the Hawking radiation has nothing to do with the Planck scale. It has to do with quantum, but it has to do with the long wavelength. I was asking about that long wavelength structure. If you had more time for the inertia, let's say, huge number of structures ready, then you could be, in principle, you could hope to probe it, would be very interesting.
And one reason why it would be very interesting is that what makes Hawking radiation difficult to understand is that it's thermal. So how could it carry all this quantum information? Well, there's a raging debate about how it's done. But the gravitational waves are not thermal. They're coherent. So in principle, if there's quantum structure at length scales of kilometers, then in principle the gravitational waves could carry that information.
Right. Yeah.
It's not thermal. It's coherent. It's not stochastic random thermal stuff. I still don't know how Hawking radiation can carry all that quantum information away, but Hawking seems to know. I'm not sure he's telling, but maybe you know more about this than I do.
Okay, well, we should continue the conversation upstairs, and thank you.